This is SpaceTime Series 22, Episode 11. Coming up on SpaceTime, new insights into exploding stars. Thousands spot an impact on the moon during the lunar eclipse. And India to launch its first manned spaceflight in 2021. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have obtained the most detailed observations ever undertaken of the first moments of the death of a star in a thermonuclear supernova. The observations, reported in the Astrophysical Journal and the Astrophysical Journal Letters, were obtained using a unique combination of ground and space-based telescopes, providing the final moments of a star's life in unprecedented detail. The event triggered a supernova called SN22E11, 170 million light-years away, in a spiral galaxy called UGC 4780 in the constellation Cancer. The cataclysmic stellar explosion was discovered back in February last year by ASSASSIN, the all-sky automated survey for supernovae. One of the study's authors, Dr. Brad Tucker from the Australian National University, says these new observations will help astronomers try to solve the mystery of exactly how stars explode. Okay, so what do we know so far? Well, thermonuclear or Type 1a supernovae are caused by the catastrophic explosive destruction of a dead star called a white dwarf. White dwarfs are the stellar corpses of sun-like stars. Stars shine by fusing hydrogen in their core into helium. When these stars run out of core hydrogen, hydrostatic equilibrium, that is the balancing act between the outwards push of nuclear energy and the inwards push of gravity, suddenly ceases, and gravity wins, causing the star's core to dramatically contract and compress. Now, as the star's core is contracting inwards, its outer gaseous envelope is expanding outwards, where, now being further away from the core, it cools and turns the star into a red giant. Meanwhile, the inwards compression on the core increases temperature and pressure, eventually getting hot enough to ignite helium in the core, causing it to begin fusing into carbon and oxygen. Now, like the hydrogen before it, the helium in the core will eventually run out. But because sun-like stars don't contain enough mass to cause the carbon and oxygen in the core to fuse into even heavier elements, this nuclear fusion process ceases and the star dies. The dying star's outer gaseous envelope begins to separate from the core and float away as a planetary nebula. The now exposed white-hot stellar core, which we now call a white dwarf, is left behind to slowly cool over the eons of time. This is the ultimate fate that our local star, the Sun, will experience in about 7 billion years from now. But the thing is, most stars aren't solitary objects like our Sun. They're in multiple star systems. And if a white dwarf is in a close binary system with a companion star, its gravitational pull can start dragging material off the other star, increasing the white dwarf's mass. If enough mass accretes onto the surface of the white dwarf, that can trigger a sudden explosion, causing the white dwarf to dramatically brighten, creating an event called a nova. However, under the right circumstances, far more mass will fall under the white dwarf, triggering a far larger thermonuclear explosion, powerful enough to completely destroy the white dwarf in an event known as a Type 1a or thermonuclear supernova, an explosion bright enough to be seen across the universe. The merging of two white dwarfs can also trigger these thermonuclear supernovae. Now, Type 1a or thermonuclear supernovae are important because they all explode at roughly the same mass, about 1.4 times the mass of our Sun. Because they're all exploding with about the same mass, they're all exploding with about the same level of brightness, and consequently they can be used as cosmic distance markers across the universe. In fact, these Type 1a supernovae were instrumental in the discovery of a mysterious force called dark energy, which is causing the expansion of the universe to accelerate. For their observations, Tucker and colleagues used NASA's planet-hunting Kepler space telescope during the final days of its mission before it ran out of fuel and was retired. Instead of hunting for planets, Kepler, under its K2 mission, was operating as a supernova cosmology experiment. And the observations it's obtained of these supernovae, including SN2018-OH, have been quite exquisite. In the case of 2018 SNOH, Kepler was able to provide images every 30 minutes, starting just before the explosion occurred and all the way through and past its peak brightness. The authors were able to detect minute changes in brightness in the star's explosion from the very beginning of events. At the same time, ground-based telescopes were able to detect changes in the colour and composition of the dying star. Tucker says the combined data from all these telescopes allowed astronomers to achieve something they had hoped for, an unprecedented observation from the very onset of a star's death. In fact, prior to Kepler, it was nearly impossible to study the early stages of a stellar explosion. It sort of began, you noticed it, and you slewed your telescopes towards it. The Kepler observations has changed all that. A typical Type 1a supernova brightens over the course of, say, 3 weeks before gradually fading away. But this supernova was different. It brightened extremely rapidly in just a few days after the initial explosion. That's about 3 times faster than a typical supernova at this time period. As I mentioned earlier, the thing occurred 170 million years ago. It's scientifically interesting because this increase in brightness deviates from expected behaviour. This early bump in the light curve requires an extra source of light. And the question is, where does that come from? The Dark Energy Camera at the Inter-American Observatory in Chile and the Pan-STARRS-1 Panoramic Survey Telescope and Rapid Response System in Hawaii revealed that the supernova was gleaming blue during this intense period of light. That's an indication of extremely high temperatures, billions of degrees hot. Tucker says some theoretical models propose that the shock wave from the exploding white dwarf ran into the companion star, the one donating the matter, creating an extremely hot and bright halo, which could account for the added brightness and heat observed. In this scenario, the observation of the excess light would be very dependent on the viewing angle, which may explain why it's not been seen in all supernova observations. However, another possibility is that light from this supernova comes from the radioactive decay of heavy elements such as nickel-56, which tend to be at the centre of the star. But if nickel accumulates on the surface during the explosion, its radioactive decay could also generate excess light at an early stage of the supernova. It could even produce a double detonation, in which a small explosion on the surface triggers a second explosion, which then consumes the entire star. Still another possibility is excess light being emitted when the shockwave from the supernova heats a large shell of material just above the stellar surface. Colour information from early ground-based images will be crucial in distinguishing between these different possible hypotheses. Still, the blue colour in particular agrees with the scenario in which the supernova interacts with a companion star, and it's harder to explain with either nickel on the surface or the heating of circumstellar material. Now, all this is significant because it favours one of 2 general models for how type supernovae occur, and astrophysicists have been debating these models for decades. In the single degenerate model, the white dwarf accretes matter from a normal companion star, that is, until it reaches a certain limit, the Chandrasekhar limit of 1.4 solar masses, and then explodes. But there's also the double degenerate model, in which the excess mass, that's that 1.4 times the mass of the Sun we keep talking about, results from the merger of 2 white dwarfs. So far, SN 2018-OH is consistent with the single degenerate model. But there are other supernovae out there which have been observed which show strong evidence against the normal companion star. So it's still very much an open question. The latest results show that a range of star systems can cause these explosions. Finding out the frequency and distribution of this kind of Type 1a supernova would help refine the models used in cosmology to estimate the rate of the expansion of the universe. Tucker says the now-retired Kepler Space Telescope has totally changed science's view of the universe, showing just how common planets are around other stars. But it's now also revolutionised what science knows about how stars end their lives in thermonuclear supernovae.
We've been using Kepler for a long time, and we've been trying to find stars that explode. And one of the cool things about it is that Kepler is famous for finding planets around other stars because it stares at the same patch of sky every 30 minutes. And what we realize that is we can use Kepler and stare at tons of galaxies, thousands, tens of thousands of galaxies, and to wait for a star that exploded. And when the star exploded, hopefully we can catch that initial stages of how the star detonates and all the cool science that happens, because this is often missed from the Earth. The Earth we're only observing every couple days. We have weather problems, sky problems, so we often miss these critical early stages.
You sort of see the blast when it's already happening.
Exactly. It's already detonated, it's already exploded, it's already brightening, but yet all that cool physics stuff, how it explodes, what's happening, information about the actual star, all happens within the first minutes to hours of these explosions. And so we saw a certain type of supernova, a type 1A. So these are white dwarfs, like what our sun will be in billions of years, that explode. And it's always been theorized that they involve a couple different ways of how they actually explode. And one has been that there's another nearby star close to it, and the gravity of the white dwarf kind of pulls off the gas in the atmosphere or the photosphere of this other star, puts it around itself, reaches a critical point where it can't sustain its extra weight, which is the Chandrasekhar limit of 1.4 times the mass of our sun, and explodes. And when it explodes, it releases this big shock wave that goes out into space. So what we saw with the star explode, we actually saw the shock wave produce because we saw the shock wave slam into this other star and cause the star to kind of really light up, essentially, and then get shoved out of the way, all within about 12 to 24-ish hours after the initial explosion.
So you not only got to see the initial shock wave of the explosion, but you could see its impact on the companion star.
That's exactly right, and this has been something that has been
long
sought after. Yeah, exactly. It's this is 1A type 1A supernova have been long theorized to have been caused by this mechanism, and people have looked for it and never found it. And when we used the Kepler Space Telescope a few years ago, we found 1As that exploded, and we distinctly didn't see the shock wave, and we concluded that it was because two white dwarfs actually just ran into each other and exploded. And so by seeing this shock wave, not only did we confirm that essentially another star, something like a red giant, had its atmosphere pulled off and pulled onto this white dwarf. But now that type 1A supernova can actually be produced by different systems. Two white dwarfs coalescing, or a white dwarf pulling material, sucking material off a companion star.
And what more can this tell you? Were you able to look at the composition of the progenitor star at all, work out what it's made of, and how that composition affects exactly what the Chandrasekhar limit is for that star?
So what we've been doing is doing follow-up observations. This program is quite unique. So what we did was coordinate the Kepler Space Telescope with about 45 telescopes all around the world, from Australia to China, Europe, Chile, Hawaii, the U.S., to observe it in not only lots of detail but different colors, take a spectrum, see what the elements are. And the interesting thing about it is, other than this very early explosion, it was completely what we call normal. It matched all the other type 1A supernova that we see to explode. Now, the interesting thing about that is when we looked again with Kepler before and saw two white dwarfs exploding each other, that was also completely normal. So here we've kind of concluded that the early stages causes different things to happen. But yet then over time, once that white dwarf essentially explodes, it all explodes in a uniform way, which is great because we use these type 1A supernova as standard candles, as they're called, to measure the growth and the size of the universe. But what we're now trying to figure out is, can we glean any of the other information about the exact white dwarf and the red giant? So we still have observations going on. There was another image taken with the 10-meter telescope in Hawaii last night, in fact, of this object. Because it's such an important one, we want to glean as much information from it as possible.
Where exactly did this object explode in the sky?
So it was a relatively nearby explosion at a redshift of 0.012, or 170 million light years away. And so it was a relatively nearby explosion. It was the closest supernova that we've ever had with the Kepler Space Telescope. And, this has got us really excited because there's, even though Kepler has now died, there's a new space telescope that's finding planets called TESS. Now, TESS is looking at faint or brighter objects, so closer together to the Earth, but it's looking at more of them. So what we're now turned into is looking at TESS. Now that we know there's what we call diversity in how stars explode, to now get a large enough number of these, so we can actually try and match up which supernova and which star causes which explosion and what the consequences are. Since we know there is a range, we need, of course, the classic problem of we need more.
Yeah, just to verify what you've seen and to show that this is the standard way they go off.
Exactly, and as you said, figuring out what these implications are for the growth of the universe and what it just means for how stars evolve and die. One of the classical problems we have is that if we know two white dwarfs explode, two white dwarfs crash into each other and explode, there's a slight problem with that, is it takes time for a star to turn into a white dwarf, right? Our sun won't be a white dwarf for billions of years. So if we look back and we see stars that explode only 5 to 6 billion years after the Big Bang, 7 billion years after the Big Bang, where does a white dwarf come into play? Because it takes time for a star to become a white dwarf. And more importantly, how do you get a star system that also has a bunch of 2 white dwarfs that explode? So it's always been a bit of a peculiar problem. How do we get these things as far as we see them in the numbers that we're seeing them?
Because the sun will take 12 billion years to become a white dwarf, but spectral type K star, for example, an orange dwarf, when they become white dwarfs, it's going to be even longer. And as far as we know, red dwarfs won't become white dwarfs, not for at least trillions of years.
Exactly. But yet we clearly see these explosions, and clearly we see something going on with the white dwarf. So there's simple numbers here that aren't necessarily all matching up. And so it's now a question of, now that we know we need to look in detail, now that we know we can see this shock wave, we need to see it more, because this is one of the clues, with the big stars, these massive stars that explode. We've been very good at actually using the Hubble Space Telescope to image galaxies before the star explodes to actually see the individual star. But you're never going to see a white dwarf in a distant galaxy with even the biggest telescope because they're so faint.
So does this mean that maybe the white dwarfs we're seeing now all come from spectral type F and G stars, I take it?
Yeah, that very well might have been that there's just a certain limit of what can cause, in terms of a normal main sequence star, these white dwarfs.
Universe.
Exactly. And because it also has to have that right mass, and that's the other trick, right? You can't have too big or too small, because if you only add up to about 1.2 times the mass of our sun, you're not going to explode as a supernova. This is what Subrahmanyam Chandrasekhar showed. But then if you, let's say you get above that limit, you should produce something slightly different, something slightly brighter, which we do see diversity in some of these, but not as big as that. So there's this very, it's like the Goldilocks zone for exploding stars, just not too small, not too big, not too old, not too young, that explodes in the right way
before they go off too.
Exactly, that's right. That it creates these things that we see, and we know we see them.
So where to next? Finding more of them, I guess.
Yeah, it really is finding more of them, and luckily we have tests, and with tests, because the way it's set up is we can observe it from the ground and in space at the same time. We're already finding more supernova, and we're just waiting to process the data and look through it. We even have more Kepler supernova that we're still processing, and so now it's really turning into statistics and numbers and getting these rates down, seeing if there's anything else funny that pops up, and also then calculating it through, calculating exactly the distances to these stars using our techniques and fitting light curves and measuring distances with these explosions to see what implications it can have for our cosmological measurements. Can we find a way of actually improving cosmology or our distance measurements or our understanding of dark energy, because we have a better understanding of the tool that we're using, essentially?
That's Dr. Brad Tucker, an astronomer with the Australian National University. And this is SpaceTime. I'm Stuart Gary. Last month's spectacular lunar eclipse came with a surprise for those watching it closely enough, a meteor quite visibly impacting on the lunar surface. The event on January 21st was the only total lunar eclipse this year. The eclipse was visible from all of North and South America, as well as Northern Africa and much of Europe. In fact, it's estimated that 1 in 4 people living on this planet could have witnessed this astronomical phenomenon. Towards the beginning of totality, when the moon was completely covered by the shadow of the Earth, observant observers, both those following the phenomenon on the internet and those watching directly with their own equipment, began reporting a brief luminous flash near the lunar limb. The news sent astronomers around the world into a frenzy, searching for images to see exactly what had happened. Jose Medina from the University of Huelva in Spain, who directs MIDAS, the Moon Impact Detection and Analysis System, was quickly able to confirm that an object did indeed impact the moon during the eclipse. Soon other scientists began examining the data and confirming the same results, which have now been published on the Pre-Press Physics website archive.org. The impact is of great scientific interest. See, although the moon is hit fairly frequently, in fact it's estimated that about every hour a small piece of space rock hits the lunar surface. The fact is, this impact occurred in the middle of an eclipse observed by millions of people, thereby providing a unique opportunity to study the event in detail. Professor Pablo Curatas from the University of Antioquia says something like this hasn't happened since maybe the 12th century, when a group of English monks observed what they described as fire-hot flashes and sparks. The analysis of the images suggests the flash was produced by a meteoroid between roughly 10 and 27 centimetres across. Now, depending on its composition, it would have had a mass of somewhere between 7 and 40 kilograms. And it smashed into the lunar surface at a speed of roughly 47,000 kilometres per hour. The impact produced a cloud of hot, bright material that expanded rapidly and disappeared in less than a third of a second. If the estimates are correct, there should now be a crater between 5 and 10 metres across at the impact site. Astronomers used a process called gravitational ray tracing to try and determine where the impactor came from. Their calculations suggest the meteoroid would have originated from an orbit inside that of Earth's orbit around the Sun. That suggests it could be part of the A10's asteroid group. It slammed into the Moon from either the direction of the constellation Scorpius the Scorpion or from some point in the constellation Callium the Chisel. Sadly, due to its small size, there is no record of the rock as it approached the Moon. You're listening to Space Time. I'm Stuart Gary. India says it will launch its first manned spaceflight before the end of 2021. 3 crew members will ride aboard the Gaganyaan capsule when it's launched aboard a GSLV Mark III rocket from the Satish Dhawan Space Centre on the Bay of Bengal coast. The historic flight will make India only the 4th nation on Earth after the Soviet Union, the United States and China to launch humans into space. The Indian Space Research Organisation says it will undertake an unmanned test flight of the new capsule by December 2020. That'll be followed by a second unmanned test flight sometime around July 2021, with a first manned mission then following around December 2021. The Indian government's provided more than $1.4 billion to develop the technology and infrastructure needed for the manned spaceflight project. Now, by comparison, China's Shenzhou space program, which put the first Taikonaut into orbit in 2003 using modified Russian technology, cost more than $2.3 billion. The 3.7-ton Gaganyaan capsule is a fully autonomous spacecraft designed to carry up to 3 astronauts on orbital missions lasting up to 7 days. As well as life support and environmental control systems, the capsule is also equipped with emergency mission abort and escape systems which can be initiated during the first or second stages of ascent to orbit. The capsule, or crew module as it's being called, is equipped with 2 parachutes and it's designed for a splashdown at sea. Originally, the spacecraft nose cone was designed to eventually be equipped with a docking mechanism. Attached behind the crew module will be an expendable service module designed to be jettisoned prior to re-entry. The service module is equipped with all the auxiliary systems and solar panels needed for orbital travel, as well as orbital maneuvering systems and 2 liquid propellant engines. In order to keep the overall mass of the GSLV payload to below 6.7 tons, the service module would need to have a mass of no more than 3 tons. India has invested heavily in its space program over the past decade, as it competes with other spacefaring nations for a bigger slice of the multi-billion-dollar satellite launch market. As well as launching numerous scientific, military and commercial satellites into orbit around the Earth, New Delhi's also sent scientific missions to the Moon and Mars. The Indian Space Research Organisation has 32 missions planned for this year, with a launch budget of around $4.2 billion. Meanwhile, India has launched its first space mission for 2019, placing a military spy satellite into orbit. The 45-metre-tall PSLV C-44 mission blasted off from the Satish Dhawan Space Centre carrying the Microsat-R Earth Imaging Research Satellite. The 700-kilogram Microsat-R was placed into a 277-kilometre high sun-synchronous polar orbit 14 minutes after liftoff. The PSLV C-44 launch was the first flight of the new PSLV DL variant, equipped with 2 strap-on boosters and a new type of upper 4th stage. Also aboard for the flight was the Space Kids India-built Kalamsat Nano satellite. The 10-centimetre 1.2-kilogram CubeSat was designed by for school children, and will serve as a communication satellite for ham radio operators. It carries enough battery power to operate for just under 2 months. It was deployed 103 minutes after launch at an altitude of 450 kilometres, together with the PSLV's new 4th stage, which will act as an orbital platform for the little spacecraft. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A royal commission into the management of the Murray-Darling River Basin has found that officials committed gross maladministration, negligence and unlawful actions in their failed attempts to manage Australia's largest river system. The 746-page report has made 111 findings and 44 recommendations, including a complete overhaul of the Murray-Darling Basin Plan and a call for the reallocation of more water from irrigation to the environment. The Royal Commission also found that the Murray-Darling Basin Authority has failed to act on the best available scientific evidence, and it's ignored the potentially catastrophic risks of climate change. The investigation was prompted by allegations of corruption and water theft by New South Wales cotton farmers. The recent fish kills in Western New South Wales were not addressed by the Royal Commission after the South Australian government refused the Commission's request to look at the issue. The Royal Commission found that politics and not science was driving the Murray-Darling River Basin Plan, and that there are serious doubts as to whether the current senior management and board of the Murray-Darling Basin Authority is capable of fulfilling their statutory obligations and functions. A new NASA study shows that the warming of the tropical oceans due to climate change could lead to a substantial increase in the frequency of extreme rainstorms by the end of the century. The findings by scientists from NASA's Jet Propulsion Laboratory in Pasadena, California, used over 15 years of data acquired by NASA's Atmospheric Infrared Sounder instrument over the tropical oceans to determine the relationship between the average sea surface temperature and the onset of extreme storms. They found that extreme storms, that is those producing at least 3 millimeters of rain per hour over a 25-kilometer area, formed when sea surface temperatures were above 28 degrees Celsius. They also found that, based on the data, 21% more storms would form for every 1 degree Celsius increase in ocean surface temperatures. Currently accepted climate models project that with a steady increase in carbon dioxide in the atmosphere by around 1% per year, tropical ocean surface temperatures may rise by as much as 2.7 degrees Celsius by the end of the century. The study, reported in the journal Geophysical Research Letters, found that if this were to happen, we could expect an increase in the frequency of extreme storms by as much as 60% by that time. A new study has found that teens who vape are more likely to smoke after 2 years. The findings, reported in the Journal of the American Medical Association, looked at data from kids aged 12 to 15. It showed that those who used e-cigarettes as their first tobacco product were 3 times more likely to be tobacco cigarette users within 2 years. Paleontologists have discovered a new theropod dinosaur at a dig site at a country town in rural New South Wales. A report in the Journal of the Royal Society Open Science says the new species is very similar to Australovenator and Allosaurus. Scientists say the fossils date from the late Cretaceous and represent only the third known example of a medium-sized theropod from this period. Well, if like me you're a night owl rather than a morning person and consequently have difficulty getting up in the morning, you can now blame it on your genes. A report in the journal Nature Communications has confirmed what we've all suspected. People really do have genetic traits that determine when they're at their best. The study used information based on wrist activity trackers worn by more than 85,000 individuals. That led to the discovery of some new genes associated with early risers. Sadly, it's also highlighted how night owls can be at higher risk of mental health issues, especially depression. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.